Morning, everybody. Welcome back. Let's see here. So, when are you guys taking your fifth exam? Yeah, is it 2 weeks from today? Something like that. It's not finals week, right? It's the week before finals week. That's when you will have your last exam in this class, right? But during finals week, we will be meeting. We won't be taking a final, we'll be doing the test autopsy. So again, just need to make sure, and I'll try to post an announcement about that. We are definitely in the home stretch here, last unit, moving into really our last broad topic, which is thermodynamics. Hopefully I have plenty of time to get that done. So just a couple of things about thermodynamics. I'm not supposed to admit things like this, but I don't like thermodynamics at all. It's just something that I didn't like it when I took it. I don't like teaching it. I try not to let that bias sort of come through, but I just can't help myself sometimes. I just get angry at it. So just realize that if I seem less enthused about what's going on, it's because it's thermodynamics. Part of the problem here is that many of you have taken chemistry, right? And chemists and physicists both do thermodynamics, but we do it kind of opposite of each other. And so if you remember anything from your chemistry about like the direction of heat flow, what positive and negative heat might mean, and if you haven't had chemistry, you don't remember this, don't worry. But physicists will flip that, okay? And we'll use exactly the opposite signs for stuff. And it ends up being confusing. And so I apologize in advance for this. I seriously wish that we could just give thermodynamics to the chemists and let them do it, right? Okay? And then we wouldn't have to deal with it at all. But I'm not in charge, and smarter people than me say that we should still keep teaching it, so we will go for it with that. One of the things that I am going to do to shorten the pain of thermodynamics is chapter 13's got a lot of math in it that just really isn't necessary at this level. So for chapter 13, it's going to be concept only. I would caution you even against even really looking at it. Like what I present in class will be enough for that chapter. Normally, you're on the hook for everything in a chapter, even if I don't talk about it, but when it comes to chapter 13, we'll go with what we talk about together, okay? So just keep that in mind. 12 and 13 are sort of, in my mind, a combined chapter in what's going on. So what I'd like you to do right now is turn to your neighbors and see if you can define all three of them, and more importantly, what's different about these three things. I'm going to give you like a couple minutes to do this. Go ahead. Think we got it? Okay, so what's temperature? Okay, how hot or cold something is? I mean, it could be heat, it could even be thermal energy. It's not real specific.
Is it a type of measurement?
So is it a measurement? Like when we think of temperature, we often think of like a thermometer, don't we? Like take a digital thermometer out and measure the temperature somewhere, or we go check the weather, or we look at our phone or our watch or whatever, right? It tells us the temperature, right? But the question I'm asking is not so much like, is it a measurement, but like, what fundamentally is it? And how is it different from the other two? So let's maybe pause on temperature here. What's different between temperature and thermal energy? Or even heat for that matter. These terms are often used sometimes interchangeably, right? We'll talk about changing the temperature of something. We'll talk about heating it up, cooling it down, right? But there are very specific ideas attached to these. So let's start with thermal energy. Thermal energy is the total energy something has because of the motion of its molecules, right? This table has a thermal energy. If I was able to measure the thermal energy of every single one of the molecules in this table and then add all of those up, I would have a total amount of energy that is contained within the wiggles and jiggles of all the molecules in this table. So thermal energy represents a total, whereas temperature is a measure of the average energy per molecule in a substance. So Ryan kind of hit it on the head right there. It's this measurement, right? So it's really difficult to directly measure the total energy in something. So as an idea, it's really useful, but in a practical sense, we don't go and measure the total energy. But it is actually pretty easy to measure the average energy in a substance, because not every molecule in this table is going to have exactly the same thermal energy. Some are going to have more than others and all that sort of stuff. But if we can figure out the average, again, in a practical sense, we never just, do some statistics and find the average. We take a thermometer and we measure something, right, with that thermometer. It just turns out that that measurement is a measurement of an average energy per molecule in a substance. So if thermal is a total and temperature is an average, what's heat? A lot? A loss? A gain? This is one where you are going to get a little bit frustrated, maybe with me and the book and physicists in general. The world typically uses this term wrong, and scientists have adopted the sort of popular way of doing it, which is really bad. Because heat is energy transfer. And it requires energy moving from one object to another. So implied in heat is this idea of motion or movement or transfer. And you will see in your book, you will hear me say it, we will talk about heat transfer. Well, what I just said was energy transfer. Right? Like heat, we'll talk about the specific heat capacity of things, which makes it sound like heat is something that's contained in an object. That is not what heat is. That's thermal energy, right? So heat is thermal energy that is moving somewhere. It's going in or out of the system, the object, whatever. And so to talk about the heat that something contains is not the right idea. Even though we'll often talk about the heat in something, right? When what we really mean is that it has a lot of energy. So sorry for the squirrely nature. So thermal energy and temperature, definites, like can hit those on the head. Just watch out for heat every once in a while, right? You want to be careful about what the problem or the book or the video that you're watching is trying to talk about. So let's take a look at this picture right here. Okay, so I've got two identical containers sitting on the same stove, right? It's just one of the containers has more water liquid in it than the other. What I want you to do, okay, is again together, just over the next minute or so, is I want you to try to determine which of these has the higher temperature, which of them has the higher thermal energy, and which of them has the higher heat. Go. Your choices are left or right. Yeah. Okay. So of these three, temperature, thermal energy, and heat, which one's the easiest to sort of identify right off? Temperature, right? And how do you know which one the left one's hotter? The thermometer, right? Right? Like you just, okay. That thermometer is reading a higher temperature. And so we would conclude that if we took a water molecule from the left-hand side and a molecule from the right-hand side, on average, the one on the left-hand side would have the higher energy, right? Okay, so temperature we can read right off the thermometer. Let's tackle thermal energy, okay? Which of these has more thermal energy? Could it be the one on the right? Remember, thermal energy is a total, right? So let's push this one to an extreme because the picture is actually a little bit hard to tell. But let's say that I had like a coffee cup's worth of boiling water, okay? And water boils at 100 Celsius, 212 degrees Fahrenheit. And then I have an Olympic-sized swimming pool, okay? So that's 50 meters by 25 meters by whatever, about 3.5 meters deep, okay? And it's frozen, solid. Which of those two has the higher temperature, my coffee mug or the pool? Coffee mug, it's boiling, right? It's a higher temperature. But which of those has more total thermal energy in it? The pool. Even though every water molecule in that pool has a much lower energy than the water molecules in the boiling water, there's just a lot more of them, right? And so the total is going to be bigger. So thermal energy, calculating the total thermal energy something has can be a daunting task, and we have to consider lots of things. Here, I mean, I would go with the right-hand side. Yes, again, lower average energy, but it looks like there's at least 3 times as many molecules, right, of water on the right-hand side. So I'm guessing it would probably have more total thermal energy than the one on the left.
So if the one on the left has like 3 times the amount of temperature, would it be kind of...
Yeah, it doesn't quite scale like that, and I'm going to skip over a lot of that stuff in chapter 13 because it gets really kind of esoteric in how molecules vibrate and things like that. But generally, you just kind of want to look at the amounts, right? And then if like if these temperatures were like this and the amounts were the same, obviously temperature would be higher on that side. It would also have more thermal energy. We're not going to try to quantify that too much. That's going to be one of the things we're going to skip over together in class. If you're going into a field where you really need to know that, then you're probably in the wrong class. That's more physics 4C stuff that we would get into. But it's a decent question. It isn't quite one for one. All right, what about heat? Which one has more heat?
We're not really seeing them transfer any energy.
Yeah, okay, so it's kind of a hard, it's the wrong question to ask, okay? Because heat isn't something that's contained. We can infer that since they are on the same surface, the same hot stove, that the amount of energy coming out of that stove going into the material is probably the same rate of energy movement. So we could say it's the same, or we could just say, well, that's a silly question, Mr. Balogh. Heat is not something that is stored, right? Heat is a transfer. We'd have to know a lot more information about what's going on there. But again, just trying to underscore that heat is movement of things, not necessarily like a quantity of stuff. All right, so there's another elephant in the room when it comes to dealing with temperature. And I summarized it with this table right here, okay? So, we'll talk about Kelvin in just a second, okay, right? What the heck has gone wrong with Fahrenheit? I mean, seriously. Let's pick the boiling point of water, right, okay? Who in their right mind would have picked, you know what, 212 sounds like a good number. Freezing point of water, we'll call it 30. Does anybody know what went wrong here? Other than it's in the stupid unit system. Fahrenheit was a Polish scientist and mathematician, and he was concerned with finding a temperature scale that worked for like weather. Like he wanted to be able to measure air temperature and cloud temperatures, and he wanted to explain weather phenomena. Now, in nature, in our weather, yes, we do drop down to freezing during the winter, right? But we never rise to boiling. I mean, unless it's Death Valley or that's not quite boiling either, right? But like, Fahrenheit was trying to find a useful temperature scale that he could quantify weather phenomena, which really kind of only take place between about 50 degrees Fahrenheit and 95 degrees Fahrenheit, right? Especially in mid-latitude Poland in the 1700s. So what happened was Fahrenheit's scale got adopted by other scientists that then tried to use it for like boiling water and freezing and all this kind of stuff. And there's a phrase in English, it's kind of an old-fashioned phrase, but it goes something like this. Too many cooks in the kitchen spoil the broth. Like when you have too many leaders, right? And everybody's trying to say, you know, how it should be. Like every cook's got an idea of the kinds of seasonings you would put in a broth. Well, if everybody does their idea, what you end up with is mud, right? Like it doesn't taste good, the flavors don't mix well. That's pretty much what happened with the Fahrenheit scale. Fahrenheit started trying to get something useful, people co-opted it and forced it into things that it really shouldn't have been used for, and for some reason we keep using it today. Like it's kind of awkward, it really is. Okay, I mean, just look at the Fahrenheit scale. 212 minus 32, is that 100 and, is that 180? I think that's 180. Different degrees between water freezing and water boiling. It's just messed up, okay? So what does the Celsius scale do, or at least remedy for us?
Boil at 100, freeze at 0.
100 degrees, like we're straight back to the metric system now, aren't we? Where everything's by 10s or 100s, right? And there's sort of that even spread from those two kind of key points about what water does, and then we scale everything else. I mean, it's closer to an ideal, but it's not quite there. The Celsius scale does suffer from having to use tenths of a degree a lot. So like we here in the United States, we kind of know the difference between like 70 degrees and 75 degrees, right? But you'll notice that you kind of never see the weather forecast, the temperatures ever reported in decimals, right? We're gonna have 74, 75, or 76, or 77 degree high, right? They never say the high is gonna be 76.7, right, instead of 78.1, right? It's just, as far as human beings are concerned, we can't really tell the difference between two small, most people can't tell the difference between 5 degrees, let alone 1/10 of a degree, okay? The Celsius scale, okay, kind of a Celsius degree, the actual amount of temperature that's represented by a Celsius degree is much bigger than a Fahrenheit degree. In Fahrenheit, we have 180 divisions between freezing and boiling. But on the Celsius scale, we only have 100 over the same distance, right? So that means that 1 degree Celsius is a much bigger change in temperature than 1 degree Fahrenheit. And as a matter of fact, you need something like 2.2 Fahrenheit degrees for every 1 degree Celsius. So quite often, a weather forecast might tell you that it's gonna be, 24.7 Celsius, right? And so we're into a little bit more of those decimals, right? Which again, isn't so much of a big deal. Culturally, the one that you grew up with is the one you're used to. And after a while, I lived in countries where we use metric and Celsius, and it's pretty easy to get a handle on in terms of like what normal room temperature is and when it's cold and when it's, so like when people in Europe say it's 40 degrees, that's hot, okay? And how do we convert between Fahrenheit and Celsius?
Some weird fraction.
Yeah, some weird fraction. This is what I do. Hey Siri, what's 40 degrees Celsius in Fahrenheit? 104. Right? Okay? So that's how everybody should do it, okay? Used to be in the old days before cell phones, you went to the bank. For some reason, banks decided they had to tell you what the temperature was in Fahrenheit and Celsius on the little sign outside the bank. I don't know why banks decided that they were the ones that did that, but you can just convert on your calculator. But that conversion it's not a conversion factor, it's a conversion equation. Okay? And this is how you get from one to the other. If you want to know your temperature in Fahrenheit, but you're given the temperature in Celsius, it's 9/5 times the temperature in Celsius plus 32 degrees Fahrenheit. So that will get you your temperature in Fahrenheit. Okay? If you want the temperature in Celsius, and you have the temperature in Fahrenheit, it's 5 nights times the quantity, temperature Fahrenheit, minus 32 degrees Fahrenheit, okay? And that will get you the temperature in Celsius. So it's not a straightforward conversion factor. You have to use this algorithm, this function, to be able to get from one temperature to another. Okay? And then, what's going on with Kelvin? What madness is this?
The universe.
Okay. This is, as far as physicists are concerned, the perfect temperature scale. Okay? Put 0 where it belongs. Not this whole freezing point of water. Who cares about that, right? The lowest possible temperature in the universe should be where we put 0. Everything is positive after that. Okay? So what the Kelvin scale does is, number one, it gets rid of negative temperature, whatever that means, and then it sets the lowest possible temperature where it belongs at absolute 0. And temperature technically doesn't have an upper limit. Are there things that are so hot that it doesn't matter anymore? Well, yeah. The core of stars is a place where it's so hot it really doesn't matter anymore, right? But as far as absolute 0 is concerned, what's absolute zero? Like, what does that mean to have the lowest temperature in the universe?
I hear that something weird happens with time, I think.
Oh, no, it's not time, not yet, anyway. That's physics 2B. What?
Nothing's moving.
Yeah, okay. If you're sitting there saying, well, it's when all molecular motion stops, I'm gonna forgive you for that one because it's probably what your chemistry teachers taught you. That is not the case, okay? I guess we could split hairs on whether it's molecular motion. I've heard teachers teach it that all atoms stop moving, and it's like, oh my gosh, this is so wrong on so many levels. Because atoms don't move A, B, they're waves anyway. Anyway, everybody just ignores quantum mechanics at this point. I don't understand why chemists decide to pretend like they know quantum mechanics, okay? And tell you lies like that. When they have the perfect definition already at their disposal. I don't know why they ignore it. I gotta go find a chemist and figure this out because it's just a shame. Because in chemistry, and we'll learn a little bit later, what happens to a gas when you heat it up? Well, but more, even if like that's liquid changing into gas, right? Let's just heat the air up. What will it do? It'll go up. It'll expand. Its volume will increase. It'll become less dense, and so it'll get more buoyant. It will go up, right? Okay. And what happens if you cool a gas off? It condenses. It contracts its volume. So temperature and volume are very much related to each other, right? Well. Is there a limit, an upper limit to how big we can make a gas get if we heat it up? I mean, there's all the room in the universe to do it, right? But what's the lower limit on the volume of a gas?
Everything's perfectly touching each other.
Even beyond that, what's the lowest volume something could have? 0, right? Because at 0 volume, it's just not there anymore, right? Now, is it physically possible to take all the atoms and molecules in a chunk of air and push them into 0 volume? No, you can't. Yeah, well, you wouldn't get a black hole, but you would. But the atoms would run into each other, right? And atoms take up space and can't have 0 space, and so while it's a theoretical idea that makes sense. It's very possible. It's not mechanically possible to get there, but we can conceive of an idea of something squishing down to 0 volume, okay? Whereas getting as big as possible just fills the immensity of space. What's the disagreement here between Celsius and Kelvin? It's 273 degrees, right? What Kelvin and Celsius are exactly the same degrees. There's 100 degrees between freezing and boiling of water on both of those scales. So a Celsius degree and a Kelvin degree represent the same change in temperature. Okay? It's just that we're arguing about where to put 0. And so to get from Celsius to Kelvin and back and forth again, it's basically adding or subtracting 273, and if you want to be really particular about it, 0.15 degrees, okay? So it's actually normally almost all the time I and everybody else just uses 273. That 0.15 doesn't come into play too often. But just to really ram home this idea that the chemists had it right, and you don't need to reach any weird quantum anything to be able to explain what's going on here. Absolute 0 is the lowest temperature possible because that would be the temperature that a gas would have 0 volume. Again, not practically possible. We can't do that, but we can imagine that would be the lower limit. Okay. We've managed, physicists have managed to cool off a gas to 1/1 trillionth of a degree above absolute 0. So 1 times 10 to the minus was that 12 degrees? Okay, that's so really close, right? And at this point, atoms start doing really weird things, and we get different states of matter, and ultra cold physics is actually pretty interesting stuff. But in a classical sense, right, not worrying about any of that weird quantum mechanics, that's what absolute zero should be. And I don't know why we make such a big deal. All right. So let's talk about what happens to stuff when we heat it up or cool it down. This is the idea of thermal expansion. I just want to use some examples here of what we're talking about. There's equation in the book for figuring out how much something's going to change its length based on how many degrees Celsius it heats up or cools down. But what we're looking at here is a road, and this is the connector where the road meets a bridge. So you got like road surface on one side that's connected to the ground, and we've got road surface on the other side that's connected to the bridge. Thermal expansion happens in materials. It goes like this. If you heat something up, it's going to change its dimension, its length, its area, its volume. Everything, when you're heating something up, the space between atoms and molecules has to get bigger. That's what we mean by thermal expansion. And the reverse of that, thermal contraction, right? Or if we cool something down, the space between atoms and molecules. So if I have a rod, I don't have a rod. Let's pretend this was made out of metal, okay, right? And I heat up my bar of metal. It starts at 1 meter, but as I heat it up, it will increase its length. Right? If I had a block of metal and I heated the whole thing up, it would increase its volume. Okay? So why the squigglies right here? Why is the bridge not attached to the ground except attached is a loose term here. This is a place, it's called an expansion joint, where the space between the dirt side and the bridge side are allowed to expand and contract. What's going on here?
If it wasn't there, the road might tear itself apart a bit.
It would. This is exactly the same reason that there are cracks in the sidewalk, not the ones that are there because the roots are making it crack, but the actual ones that they carve into the sidewalk, right? Those expansion joints, those lines. You know the ones where you play the game, step on the crack, and you follow and break it, right? That one, right? Those are there because if you didn't put that into concrete, and the concrete sets, and say you pour it in the Fresno summer, well, what happens in the Fresno winter? We would have shrinkage, right? And without place to go, okay, without space with which to like pull apart, okay, the whole slab of concrete would crack itself up, right? As it tries to shrink, it doesn't have any place to go. Same thing as it expands, right? Without those expansion joints, there's no place, and it would just have to go. It would have to go up. The bridge side over here, the rate of thermal expansion is different because the bridge is made out of metal and superstructure and all that kind of stuff. It's going to change its shape, its length, much quicker than the road surface that's attached to the ground, because the ground is much slower to change its length based on thermal energy. And so we need these structures that allow, right, for a change in the lengths of these things so that they don't end up buckling, right, and end up being like most roads in Fresno full of potholes and stuff.
So you know how like if you forget a soda in like the freezer,
Mm-hmm.
isn't that expands?
So, because we haven't talked about water yet. Yeah, so water is going to break all of these rules, okay? Water does something strange, and we're going to get there in just a minute, okay? And I'll try to answer your question then. So the next picture is pretty fun. These are railroad tracks, right? Maybe more people would ride on the train if the tracks were like this, because this looks kind of fun. No, this is a bad day for a railroad track. These railroad tracks were poured. Most railroad tracks consist of sections of the rail line. roughly about the length of this room, they'll lay it down, but then there'll be space between the next rail. And if you go out here and listen to the train, you can actually hear the clickety-clack of the wheels as it goes over the expansion joints in the rail. Okay? Those rails can, they just change their length over the hot and cold of the day, and they just need room to be able to do that. These rails were poured, they were actually molten metal that was poured by a machine, and it's just a constant, just unending piece of rail, right? And what the engineers of this project failed to take into account was thermal expansion. And so, as you can see, it's pretty cold in this picture, right? But those rails, when it was hotter, right, tried to grow their lengths, didn't have anywhere to go along their lengths, and so just, shot sideways. And train no worky when that happens. All right, so let's see if you're doing okay with thermal expansion. I'm not playing video for you. I'm gonna make you answer a question. I know I've kind of stopped doing quizzes, but these are quiz-like, right? So they're gonna set up a situation, and then we're gonna try and see what's gonna happen.
Brass expands when heated. This thin brass plate has a circular hole in its center. When the plate is heated, will the brass expand inward? Will the hole become bigger, become smaller, or remain the same size?
Okay, so plate, hole in the middle. They're gonna heat up the whole plate. They're gonna use this burner, but you can think of it as like they're sticking it in an oven or something like that, right? What I want you to do in groups, talk to each other about it, is the hole in that plate gonna get bigger, smaller, or stay the same size? Go.
It's probably gonna get wider on the outside. Go like that. I think so. They put the hole into the plane and then the outside would probably. So I think they're just putting it on.
Right.
Or wait, the metal's expanding, that means the whole should. Because it's getting bigger.
Are they gonna heat it up?
They're gonna use there's a gas burner right there.
Are they gonna like heat it directly?
Yeah, they're gonna heat the whole.
Oh, okay.
All right. So how many of you say that hole is going to get bigger? How many of you say the hole is going to stay the same size? How many of you say the hole is going to shrink? Yeah. Okay, we're all over the place here. This is exciting, right? It's exciting. Let's see what happens.
To verify our result, we compare the size of the hole with the size of this ball, which will not quite fit through the hole. We now heat the plate.
And they do some clever video editing to make sure, because this takes like a few minutes. doing this in class is like really boring. They are heating it up.
After the plate is heated, the ball fits through the hole, indicating that the hole expands when the plate is heated.
Okay, thermal expansion means, right, that the space between atoms and molecules has to get bigger. It would seem like it almost would make sense, right? Like if we're gonna cause the space in the metal, the space between atoms to get bigger, right? Doesn't it seem like intuitive that the hole should shrink? Right? Every dimension must increase, including the circumference of the hole in the plate.
If you were to like restrict certain areas, like, is there a possibility that it can't all expand if you.
Yeah, and then it would crack,
Okay.
depending on how much heat you actually gave it. And that's again why the expansion joints need to be there, right? So in this example, right, that hole has to increase its size because thermal expansion affects every dimension of an object, right? The circumference of the hole has to get bigger, plate has to get bigger, right? Thermal expansion, that's pretty much, that's like targeting directly a misconception about thermal expansion, but now you know, right? That everything has to get bigger, including holes in things, and that sort of stuff. All right, so what the heck is going on with water? Water's pretty nifty stuff. It breaks several of the rules of thermal expansion, and it does so more or less in our favor. I'm going to explain why you are here using this graph, okay? And what I mean by that is our biology, our evolution, our physiology would have been very different, as far as we can tell, impossible, without this particular feature of water. Because water actually, it does expand. If you heat water up, it does expand. But as you cool water down, it reaches its minimum volume, its minimum contraction at 4 degrees Celsius. This means that water's density fluctuates with temperature, just like pretty much every material's density fluctuates with temperature. But in particular, water becomes its most dense at 4 degrees Celsius. That's the lowest its volume is ever going to be. Because if you keep cooling water down past 4 degrees Celsius, heading to 0, you're actually going to be increasing the volume. The reason this happens has to do with the shape of water molecules and intermolecular forces, van der Waals forces, hydrogen bonding. There's lots of really kind of cool chemistry that happens. But the upshot for us is freezing water is less dense than liquid water. In other words, what does ice do? It floats. Because it has less density than the fluid that's around it, it's going to float in liquid water. Why is this a good thing? If water behaved like everything else, in other words, the colder it got, the more dense it got, right? Its volume got smaller and smaller. How would the rivers and lakes and oceans freeze?
There wouldn't be like a water layer under that.
They would freeze from the bottom up, right? And that makes it really hard to be a fish. Doesn't it? If the medium that you are trying to live and breathe in suddenly becomes a solid, okay? Evolution would have taken a very different route, right? Or maybe you just would have a hard time getting started. I mean, we really only have one data point, right? Which is life gets started in water. Okay, you need lots of water for life to get going and all that kind of stuff. So I know that we have a very narrow field of view here, but until we find evidence to the contrary, this feature about how solid water is less dense than liquid water really comes into our favor. Because frozen water being on top, right, at 0 Celsius, what's the temperature going to be at the bottom of a frozen lake? Well, not only not 0, I can tell you exactly what the temperature is going to be at the bottom of the lake. It's going to be 4 degrees Celsius. And why is it going to be 4 degrees Celsius? Where does all the densest stuff go? The bottom, right? So, like, during the wintertime, frozen lakes up in the mountains, I can tell you, Javer, 4 degrees Celsius at the bottom, right? It might be something else everywhere else, but at the bottom, 4 degrees, because that's where the densest water ends up, right? And the fish can be happy, right, down there. So it's a matter of knowing, right, the rule, which is heat something up, volume increase, get less dense. Cool something off, volume decrease, get more dense. except for water. And where does water turn around? 4 degrees Celsius. You just always 4 degrees Celsius, assuming it's like not salt water or something, right? Standard H2O. Okay. Let's move into, which for some of you is going to be somewhat familiar territory, okay? Especially if you've taken a chemistry class. I keep mentioning that. If you haven't taken a chemistry class, please don't panic, okay? You're actually probably better off, okay? Because you haven't been poisoned by the chemist, or by me in that case. These are German packages of chewing gum, I think. But the reason I have a picture of it is because I want you to see, right, what units they are measuring the gum's caloric content. You see how it says 22 calorian, right? Okay, that would be calories in English, right? But then there is another unit that's expressed there. What is it? Kilojoules or joules. We've run into joules before, right? Joules are units of energy. And what we're going to do is we're going to talk about energy transfer, right? And how to heat things up, cool them down, and how to keep track of all of that. And since it's energy, I hope it comes as no surprise, right? Energy is energy, and in physics, our standard unit is joules. But I think we probably need to talk about the whole calories thing, because there's something fishy going on here. This is a picture that was sent by one of my students many years ago. The semester was over, okay? She didn't need to impress me or extra credit or any of that kind of stuff, right? She was on break, and she sent me an email. Mr. Balogh, she had gone to Mexico. Mr. Balogh, look! And she had sent me a picture of her coconut water, okay? She'd boxed, okay? They're giving us not only the calories, but also the joules on the can, right? Okay? And then something else was going on here, right? Why does it say 73 kilocalories up at the top per can, right? But down here it says 73 calories per can. Do we have a typo?
Oh, is human calories measured differently?
There is a difference between the dietary calorie, usually almost always written with a capital C. I've really sort of emphasized it here on the board, okay? And the scientific calorie, which is often spelled with a lowercase c, okay? Nowadays, kind of a more modern way of doing this is to represent this as a kilocalorie. But what's going on here? What does kilo stand for? It stands for 1,000, okay? So we better back up. What's a calorie? A unit of energy? Something that Americans seem to be like inordinately fixated on, right? We're always like counting calories and doing all that kind of stuff, right? So there's a definition for the calorie, okay? It's actually kind of hilarious. But a calorie is a unit of energy, okay? And this is the definition. It is the amount of energy required to change the temperature of water 1 degree Celsius between 14.5 and 15.5 degrees. What? It sounds like a chemistry definition because they're being really particular, right? Okay? The amount of energy required to heat 1 gram of water 1 degree Celsius. A gram of water is a milliliter of water, like a sugar cube sized amount of water. Okay, so imagine we can measure the temperature of that, right? We know that it's a temperature, and then we turn the stove on, we keep track of the amount of energy transferred into that water, and when we see it raise 1 degree Celsius, we go, okay, good, that's a calorie. calories, the amount of energy required to change the temperature of 1 gram of water, 1 degree Celsius, right? But that's not, I mean, it's not terribly useful, right? Okay, to know that definition. But it is useful to know that a calorie is a unit of energy. It happens to be equal to, I'll write it on here, in terms of joules, 1 scientific calorie is 4.186 joules of energy. And again, it's a conversion factor, but in terms of like a gut understanding, right, of what a joule is, that's even worse than our understanding of what a calorie is. But on nutrition labels, they use capital C calories, which are kilo scientific calories. So a dietary calorie is 1,000 times bigger than the scientific calorie. So when my Snickers bar says that it's 186 calories per serving, let's not question how I know that number so exactly. Okay? How many actual scientific calories is that? 186,000 calories? No wonder I have to work so hard to work off a Snickers bar. It's 186,000 real calories. They're trying to hide stuff from me, right? They're trying to make it sound better than it actually is. I mean, let's face it, Americans would stop eating if they knew that Snickers bars were 186,000 calories, right? But it's actually not, it's not a conspiracy or anything, right? Because the average daily recommended, this is a very loose term, and I'm skipping over a lot of good science here, but like, what sort of like average amount of calories a human being should have in a day? It's like 2,000-ish. This varies quite a bit depending on several factors, okay? If you are nursing or pregnant, you definitely want more, okay? If you're trying to lose weight, you want less. So it depends on age and some other things, and you'll want to go to the government websites or the USDA to like kind of look up sort of what your target should be for whatever goals you have in your life. But like for me, my doctors say I should be having 1,800 calories a day, right? So it's not as simple as just everybody gets 2,000 anymore. But that 2,000 calorie diet for the day is really 2 million scientific calories. The reason that nutritionists have done this is they've gotten tired of writing so many zeros all the time, right? But just realize that, right? That there's a difference between a dietary calorie and a scientific calorie that's a factor of 1,000. What's really useful though, right, is when you go to In-N-Out Burger, right, and on the menu they've listed that double with animal style fries is like 900 calories. Okay, that's telling you that one meal is almost half of your daily amount, right, of calories. So if you are keeping track of your energy intake and expenditure and all that kind of stuff, it's useful because it's all scaled correctly to each other. Right. All right, so let's talk about the other thing that comes up when we're talking about energy transfer and heating things up. And that is something called the specific heat capacity. I hate that term because heat is not something that is contained. Okay? And for whatever reason, specific heat is confused in a lot of people's minds about kind of what it is. So I'm going to take this from 2 different points of view and see if I can't help you, okay? We defined calories, right? We said it was the amount of energy required to change the temperature of water, 1 degree Celsius. Specific heat is exactly that same thing, Just swap water out for whatever material you want. How much energy is required to change iron by 1 degree, 1 gram of iron, 1 degree Celsius, right? The amount of energy required to change aluminum, right? 1 gram of aluminum by 1 degree Celsius. It's the specific heat is the calorie. It's just calories, a special name we use for the energy water requires. Specific heat is the number, you go look it up on a table for whatever material you're trying to look for. But even that's kind of a little esoteric. Okay, great. Mr. Bailey, you defined it for me, but I still don't know what it means or, like, more importantly, how to use it. Like, what does it mean for iron to have 470? They wrote it kind of funny on this table, but it's 470 because it's 0.47 times 10 to the 3, right? So it's 470 joules per kilogram degree Kelvin versus aluminum's 910, right? Okay, so what does that mean that one is bigger than the other? Try to latch on to this idea, because of all the ideas around specific heat, this is the one that has the biggest benefit. Specific heat is thermal inertia. What's inertia? Now we're going way back to like chapter 4.
Amount of energy you kind of need to really get something moving.
Yeah, it's like this idea that tries to capture how hard it is to get something to move. The more inertia something has, the more force we have to apply to it to get it to accelerate. That's Newton's first law of motion. Okay. Specific heat is the thermal equivalent of inertia. In other words, the bigger the specific heat, the more energy is required to change the temperature of that substance. It has more thermal inertia. It resists changing its temperature, okay, when you supply energy to it. So, as an example, which one is easier to heat up? Iron at 0.47 or aluminum at 0.91? It's iron. And how do you know it's iron? It has less thermal inertia. It has less specific heat. It requires less energy to change the temperature because the number is lower. Okay? So on this table that I've got up here, okay, and again, you just look these up, I'll give them to you, unless I'm asking you to find them, right? But if you need to use these, I would just give them to you, right? Of all the things on this table, what is the thing that has the largest thermal inertia? It's water, right? 4.19 compared to everything else that is like 2 and less, right? Okay? In other words, water really resists changing its temperature. You have to supply a lot of energy to get water to change its temperature compared to other materials. This makes it a good medium for like cooking because it will maintain its temperature easier. It won't be fluctuating its temperature as much. You want to try to cook those noodles to that perfect al dente stage. You really want to know that your water, your boiling water, is going to be 100 degrees Celsius and stay there. Because, as everybody knows, you cannot find good Italian food in Denver, Colorado. It's just simply impossible. What's wrong with Denver? Altitude. Okay, and what happens to the boiling temperature of water as you go up? It goes down. Water only boils at like 95 Celsius in Denver. They can't get it to 100 degrees Celsius, which means they have to cook it longer to get to that same perfect doneness. And I know what I'm talking about. I'm Italian. Okay? And it just ends up being mushier pasta. Okay? So, yeah, don't try to, I mean, I'm sure there's good Italian restaurants in Denver, but I've never found one, and I've been there a lot. All right. So that sort of, now that we, welcome to Cooking with Mr. Balogh, okay? But now that I've mentioned cooking a little bit here, let's just stop, okay? that is a cast iron frying pan. It is actually one of my favorite cooking vessels of all time. Cast iron is fantastic stuff, especially if you know how to work with it. It will become nature's nonstick surface. You don't need a nonstick pan. But one of the things that's nice about iron is that it does heat up and cool off fairly quickly. Aluminum, on the other hand, will take a little bit more time, but it's a cheaper material. Oftentimes you go down to like Walmart or Target and you're buying a cheap frying pan, it's just gonna be made out of aluminum. It's cheaper than iron, it's lighter than iron, but it does take a little bit more time to get it to heat up and cool and subsequently cool off. And if the thing that you're cooking requires like a sear and then a slow, you wanna be able to change things fast. More fancy pans will be made of multiple materials, right? You can see this fancy pan here has got a copper core with aluminum and stainless steel in it. See copper on this list at 0.39? Copper will rapidly change its temperature. It's got very low thermal inertia, so it'll respond really quick to turning the stove up or turning the stove off. But you can sandwich that copper core with copper is a very soft metal, and it's like really sticky metal too. You don't really cook eggs on that. So you can combine it with other materials to take advantage of the different materials' properties, right? That's going on in there. But if you want the biggest bang for your buck, cast iron's the way to go. And if you treat your cast iron correctly and season it properly, it's really not going to be a sticky thing. I can't recommend it enough. But when you get a real job, you can afford the fancy pans. They work really, really well. All right, let's get rubber to the road here and talk about how we're going to deal with keeping track of heat, the energy it takes to change the temperature of an object. In physics, we use the capital letter Q to represent heat. And it's going to be dependent on the amount of material, the mass of an object, its specific heat, and the change in temperature that caused the heating in the first place. Sometimes you'll see this written as delta Q. A lot of times physicists will drop the delta on the Q because heat requires an energy transfer. It is a change, right? But we're not like changing the heat. Heat is the amount that went in or out and we can keep track of it based on how the temperature changed. So that's kind of what our notation is doing there. And we can keep track of all the heats that are going in and out of stuff in a particular thermodynamic system. And that word system in thermodynamics kind of has a very specific idea that we're going to talk about on Thursday. But when it comes to the science of calorimetry, the system is going to be whatever objects we have that are gaining or losing heat. So I want to do an example of this. Straight up example to show you how to do calorimetry, okay? And I want to help you by bringing back things that we've already studied, right? What we are about to do really isn't new. I know I've dropped specific heat on you, but that's an energy. We've dealt with energy before. And calorimetry problems where we are keeping track of energy flow, they are conservation of energy problems. And we've done conservation of energy before. The good news is that we don't need to pick 0. 0 degrees is pick forth. And we don't have to worry about like final and initial point. There will be final and initial temperatures in our problems, but there isn't like a physical point that we have to assign to it. What's left then? Like, what are we doing? Every calorimetry problem is always this problem. Add up, sum up all of the heats, all of the energy transfers, and when you do that, you should get 0. What we're saying is, when we're doing these problems, we are going to assume that the objects involved are perfectly insulated from their environments. In other words, we are not going to let energy, thermal energy, flow into like the universe or come from the universe into our system. The system itself, whatever it is going to be isolated. It's going to be all by itself. The system in this problem right here consists of a sample of metal, a copper cup, and water. Figure out what the things are that are in the problem. I like to draw a picture. So I'm going to have this copper cup, okay? And the copper cup's going to have water in it. And the sample, the 100-gram sample, is going to be put in there, right? So my system consists of those three objects and nothing else. We're going to assume the rest of the universe doesn't exist. What this looks like in practice is that you have an insulated material, okay? Something that's keeping the energy from flowing in or out of our system. All right. And again, that's what the equals zeros means. So what you want to do, again, in identifying this system and getting kind of a picture down, is you want to be able to write down what all the Q's are going to be. And there's going to be a Q for every object in the system. There's going to be a Q for the cup, and then there's going to be a Q for the water, and then there's going to be a Q for this unknown sample. Chemistry does this differently. Chemistry does it confusingly. Like Q cold equals negative Q hot or something like that, right? Don't do that. It's conservation of energy, right? And what's more, the delta T's are going to take care of the positive and negative signs for us. There's no guessing here. We are going to add up all of these Q's and get to zero. What does that mean about at least one of them? Something has to be negative, right? But I'm not going to artificially go in there and change it. I'm going to let the change in temperature do that for me. And so, Q for the cup. Well, that's mass of the cup, specific heat of the cup, change in temperature of the cup, plus mass of water, specific heat of water, change in temperature of the water. Plus, and what am I going to write down for the unknown? Mass of the unknown, specific heat of the unknown, change in temperature of the unknown. What are we being asked to find? Specific heat of the unknown sample. It's sitting right there, right? So now I have to do some algebra, right? I've got to move some stuff around. I'm going to move mass of the cup, specific heat of the cup, change in temperature of the cup from one side of the equal sign to the other, which means it becomes negative. And then I'm going to move the mass of the water, specific heat of the water, change in temperature of the water to the other side of the equal sign. That leaves you with mass of unknown, specific heat of unknown, change in temperature of unknown. And then I can divide both sides, mass unknown, change in temperature of unknown, so that they cancel on this side, leaving me with the specific heat of the unknown being that. Let's check and see if I know all of this stuff. Do I know the mass of my cup? Yep. Do I know the specific heat of my cup? They tell me it's copper, so I can go look that up. Do I know? Okay, so let's see here. I know that the mass of my cup is 0.075. What just happened there? Converted to kilograms. You're going to want to make sure you do that, okay? And then I go look up the specific heat of copper, okay, and it's 387. And again, I'm putting all of this in standard physics units, right? And then, let's see here, change in temperature of my cup. Remember, change in temperature is a final minus initial. Change in temperature of my cup is a final minus an initial temperature. What's the final temperature of my cup? 25 degrees Celsius. What's the initial temperature of my cup? 20 Celsius. So I just plug those in. And there's a minus sign on that. Okay? And then I'm going to subtract off and do exactly the same thing for water. How much water have I got? 0.150. 150 grams is 0.15 kilograms. Water specific heat is 4,186. And then the water also ends at 25 and starts at 20. Undergoes the same change in temperature as the cup. And then we're going to divide all of that by the mass of my unknown, 0.1. And then change in temperature for my sample, change in temperature for my unknown. What's the final temperature of the unknown? It's 25. The system, all three things end at the same temperature. They all come to equilibrium. But where does it start? It starts at 100, doesn't it? Ooh, what's 25 minus 100? It's a negative 75, and that's where that negative Q would come from, right? So I have a negative number on the top, I have a negative number on the bottom. That's going to be a positive number overall, and the specific heat of my unknown turns out to be 438 joules per kilogram degree Celsius, or approximately that of iron. Please don't overcomplicate calorimetry. Calorimetry is conservation of energy. You're adding up all the energies and setting it equal to 0. Let the change in temperature figure out what the signs are going to be for you, right? Plug in your values and away you go. Need to check something really quick, because I failed to do it this morning. Okay. Tomorrow's lab is listed just as lab on the schedule. We're scheduled to do our thermodynamics lab, calorimetry. We're scheduled to do that next week. I've taught you enough that we can do that lab tomorrow. And then that would leave next week as like a grasp, like get your homework done type week. So I'm going to call an audible here. Let's do our thermodynamics lab tomorrow. Okay? We're going to do calorimetry tomorrow because I've just shown you how to do calorimetry. And we'll do that calorimetry lab tomorrow so it's fresh in our brains, right? And then next week we'll have open lab time to be able to catch up on all of our homework and do all that kind of stuff. Okay? So tomorrow, thermodynamics lab. You already have that lab packet. If you don't have it, don't panic. I'll have a copy for you. Have a fantastic rest of the day.